So I want to wrap up our talk on exploratory factor analysis and really our content material for the semester with a few last odds and ends, which are important to go over, and then end with some talk about confirmatory factor analysis, which really isn't part of this class, but we can still talk about a little bit. So the three things we're going to go over are what we call Heywood and ultra Heywood cases. So these will come up and you should know what they are. We'll talk a little bit about oblique rotations, which we haven't gone into huge detail about, but are good to know about, and then a little bit on confirmatory factor analysis. So many estimation methods for EFA, especially algorithmic ones like the principal factor solution, maximum likelihood methods, can lead to odd, uninterpretable solutions. So one of the common ones that you run into is called the ultra Heywood case. So in the ultra Heywood case, one or more of the communality values, h squared, is estimated to be greater than 1. So this is based on the correlation matrix. So this is the standardized version, not based on the covariance matrix. In that case, it could be greater than 1, but the standardized version based on the correlation matrix should never be greater than 1. A Heywood case is where a communality is exactly 1. So why is this a problem? Well, another way to remember and to sort of think about things is that the h squared is squared multiple correlation and r squared between one variable and each of the other variables. So by definition, it needs to be restricted to being inside of 0 and 1. It also raises a second issue, which is that it implies that the specific factor, the psi element, is less than 0, or that the specific factor has a negative variance, which is another thing that should not be possible. Negative variance is not something that should ever be possible. And so, of course, this just is something that can come up in the algorithmic estimation methods because these don't technically impose any restrictions on what the values can be. And so there can be unusual cases where you get these values that are sort of should be out of bounds. So some common causes might be bad starting values in an iterative algorithm, like the principal factor solution we talked about. Choosing a bad value for m, so estimating too many or too few factors, maybe having too small sample size in your data, or having data that's not suitable to factor analysis for some reason. There can be other reasons too, and we're going to see one in a second. But this is something that comes up and you need to be aware of. So the simulated data I provided last week will actually lead to ultra Heywood case under principal factor solution. So when we use the principal factor method with two factors, we get these fun warnings. And down here you see ultra Heywood case was detected. Examine results carefully. So we can pull out the communality and uniqueness estimates from our results. And here you see we have a communality for calculus that's 1.02, which also implies uniqueness for calculus that's 0.17. Notice that the uniqueness is always 1 minus the communality. So this is especially kind of interesting because this data was explicitly simulated to look like it was driven being driven by two factors. I simulated this data to look like a two-factor structure. And I think if anything, what's going on here is the unrealistically high correlations between the variables as I simulated them caused this issue. I did that to really make the sort of principal component solution last week pop. I wanted it to be very clear and obvious, which isn't always in principal components analysis. So I think that's what's causing the algorithm to trip up here. So one thing you can always do if you run into an ultra Heywood case is try a different estimation method, especially in a case where you think that you have the right factor solution. So here we know that the two-factor solution should probably be right. If I switch over to maximum likelihood, I no longer get the ultra Heywood case here, although the communality for calculus is still extraordinarily high. This is essentially implying that all of the variability in calculus can be captured by the correlations between calculus and the other variables. So one thing we shouldn't do when we get an ultra Heywood case is interpret our results. By definition, well, when we have an ultra Heywood case, we know that our model results cannot be correct. So you shouldn't really go and interpret the factor loadings. You shouldn't do anything with the model. You can mess around with estimation methods. You can do some other stuff, but you should treat the model as having the model estimation is having failed. You can think of this almost like as a model that didn't converge properly. It doesn't necessarily mean that your proposed factor structure is wrong or that your theory is bad, but it does mean that the estimation failed. So that's ultra Heywood. So now we're going to look at oblique rotation. So far we've looked exclusively at orthogonal rotation methods. This implies that no matter what, we never ever want to allow any of our factors to be correlated. So the different factors in our data have to be orthogonal to one another or uncorrelated. And this raises an obvious question, which is whether this is a reasonable restriction. So do we really think that the two IQ factors in the WACE R data are completely uncorrelated? One way to relax this restriction in a factor model is with what's called an oblique rotation. So one of the most common is this Albumin rotation. This is actually the default rotation method in the psych package, I believe. And using an oblique rotation will produce a factor correlation matrix. So we can access this output as phi. So here I'm going to use the Albumin rotation for my, this is based on the Wechsler data. So now we're allowing our two factors to be correlated, and we see if we do this and we use the Albumin rotation, we actually get a very high correlation between the two factors, which isn't surprising. The two IQ factors should be probably pretty highly correlated. So we see that they're correlated by about 0.68. So we can now look at the factor loadings to see how it compared to our orthogonal methods. So here we see we get a pretty similar set of results. So we still get high factor loadings sort of broken down by these two sort of groups, although similarities is a little bit low now and arrangement's a little bit low now, but it's still pretty clear that we're getting a similar pattern. But one thing to also notice is that the off loadings, so like information on ML2 on the second loading, or block on the first loading, or arrangement on the first loading, these are now really low. If they're missing, it means they're below 0.1. This is sort of something that's, I think, a little bit more common when you use oblique rotations, is that it really gets rid of this sort of cross correlation or the cross loadings between the factors in cases like this. So there are advantages and disadvantages to oblique rotation. So advantages are that it allows the factors to be correlated, which is in psychology extremely common. This isn't always this isn't common in all fields, but in psychology we tend to expect that the factors within person are going to be correlated, and that there is some information that's driving the similarity between different factors. That's sort of not strictly orthogonal, and it can help us sort of clean up these sort of off factor loadings or the cross loadings. Some disadvantages are that it's a more complex technique. It's not as statistically simple as orthogonal rotation. So orthogonal rotation is really nice because it's very clean and easy. And it can be more difficult to interpret. So if two factors are correlated, how can we really be sure that they're fully distinct from one another and not actually just one factor that we're sort of mistaking for being more than one? So in general, the consensus isn't totally settled on this, but I think the trend is definitely pushing towards oblique rotations. So I think it's pretty common that you'll see oblique rotations in factor analysis these days, especially in psychology. But they tend to work better the more theory you have. When you're really doing like fully exploratory work and you don't really have much theoretical expectation, like you're sort of just probing some data, you'll tend to want to keep your methods a little bit more restrictive. You may want to do pure PCA, and if you do factor analysis, you probably want to stick with orthogonal rotation. So the last subject I just want to wrap up the semester with is just to briefly touch on confirmatory factor analysis. So whereas PCA is the most data-driven possible approach we can take to probing the sort of dimensionality structure of data, confirmatory factor analysis is the other extreme. It's the most theoretically driven. And EFA is sort of in between. EFA builds on PCA by restricting the number of factors we interpret. So in PCA, we have the same number of factors as variables. In EFA, we take m less than p factors and say that those are driving the variability in our data. CFA imposes an additional restriction beyond this. So it's not just restricting the number of factors we interpret, it's also restricting something else. So in EFA, we make no assumptions about which factors drive which variables. We estimate all factor loading. So we say that every factor has some kind of loading on each variable. In CFA, we don't just restrict the number of factors, but we also restrict these loadings. So for the most common type of CFA model, each factor will load on only one variable, and then we restrict the cross loadings to be 0. In EFA, we do not do any restriction of the cross loadings. So this is the biggest sort of conceptual difference between CFA and EFA. And while they share a name and are mathematically related, CFA was actually developed in a sort of independent school of thought from EFA. So it really comes out of the tradition of structural equation modeling, or SEM. And in R, CFA and other SEM techniques work under the Lavon package. So it's a totally different sort of setup for doing CFA, and really not something that's easily taught just in sort of like a short lecture at the end here, or even a couple lectures. It's really a totally different technique from a lot of what we've learned so far this semester. And so the way Lavon works in R is you sort of pre-specify your model with some written syntax, and then you enter that into the estimation. So first, I'm going to show you how I would do a CFA for the verbal and perceptual organization factors based on this IQ data. So the first thing I need to do is set up my model. So this is just pure syntax. It's just like, this is just like a string object that defines my model, where I'm saying V is equal to information comprehension, similarities, and vocabulary, and P is loading onto completion, block, arrangement, and object. And by default, CFA is going to assume that the two factors are correlated. So it's also another difference is that in EFA we at least start with this orthogonality assumption, whereas in CFA we don't start with that assumption. We assume that the two factors are correlated. So then I can use the CFA function in Lavon to fit my model and check it with the summary function. And the summary function produces a very large output of diagnostics, which I forgot to bring up, but I will in a second. So obviously this won't all fit on the screen, but let me jump over to my R console and I can try to show you a little bit of what this looks like. So where is the, here it is, okay. All right, so here is the summary output. Let me see if I can get it a little bit better onto one screen. Just give me one sec. Okay, this will be a little bit more readable. All right, so I'm asking for fit measures and standardization here as extra things. These won't come by default. So you get lots of stuff here. So at the top, you get a little bit of callback about how the model worked. You get a chi-square test, which is just like an EFA, always going to be almost always going to be rejected. It's actually not that big a chi-square value. It's pretty good. Oh, this is a slightly different model. I see why. I don't know what happened here. It's different data. Let me rerun it. Okay, this is the actual result. Okay. Yeah, so here we get a fairly large chi-square value. So we're going to get a small p-value. We get some different model fit statistics. So I'll walk through these on the next page, but this is where you get them from. So you get the CFI and TLI here. You can get AIC and BIC, but we're not too often going to be too worried about those. We're going to get RMSEA here and SRMR. So these are common fit statistics for CFA models. And then we're going to scroll down a little bit. We're going to get, so this latent variables table, these are our factor loadings. So by default, it's going to set the first factor loading for each factor to be 1. And then it's going to give you the other ones. And notice that how we don't have any cross loading. So we only have only these first 4 variables load on V, and these other 4 variables load on P, but they don't load onto each other. So there's no cross loadings here. Then we get this covariances table. This is the estimated covariance between the 2 factors, which again, by default, we do allow the 2 factors to be correlated. So we get our standardized version here. So this is our correlation. So the 2 factors are once again estimated to be very highly correlated, even higher than in the EFA model. So 0.76 here. So then we get the variances, not just of our variables, but the factors. So these are the model implied variances of each variable and the 2 factors. And over here under the standard column are the model implied standard deviations. That's what, once again, this is not the actual observed variances and standard deviations. These are the ones implied by the model. So that's a sort of quick overview of the CFA Lamont output. And so here's a little bit about evaluating the models. The latent variables selection provides the factor loadings, which again, that's where you interpret some of the results, but the way you assess the model itself are often with these fit statistics. So RMSEA, you usually want this to be below 0.05 or 0.06. SRMR should be below 0.08, and TLI or CFI, which are related to one another, should be above 0.95. So in our example, RMSEA was 0.11, which is pretty big. That's not great. So the model doesn't actually fit that well here, according to the CFA results. The SRMR showed good fit. The TLI and CFI were kind of borderline. Overall, I would assess this as not being a great result for this model, and that this CFA model does not actually fit the data that well. Some of the other outputs that I mentioned again, you get the covariances between the factors and then the variances, which is the model implied variances of each variable and each of the factors. And so this was a really, really sort of quick run through of an introduction to CFA. In general, what you're going to do is you're going to do EFA when you're starting out, when you're first starting to evaluate the structure of several correlated variables. So if you've never really done a factor analysis before, you're going to start with EFA on a particular type of structure of data. And then after an EFA, it's common to do CFA as a separate study. So you do an EFA to sort of probe the structure of the data, then you collect more data and do a CFA and see if that can sort of validates your results. You don't usually do an EFA and then a CFA on the same data set. That doesn't really make sense because you're just confirming the results you got from the EFA, you're not actually validating them. So if you're interested in learning more about CFA, it's covered in much more detail in the structural equation modeling class, which will be offered by Dr. Chan next spring. Thank you to everyone for watching and sticking through these videos. I hope you all have a wonderful summer. Good luck on your final assignment and on the final.